Okay, thanks a lot, Klaus. I just want to show you, give you a flavour of the kind of experiments we're doing and the kind of the data we have to do that we can analyze our experiments properly. As Klaus said, we're testing the nanomaterials under most realistic conditions, and for example, we do some spiking experiments in a pilot wastewater treatment plants. That what you see here, it has a denitrification stage, a nitrification stage, a secondary clarifier. So it's a classic activated sludge process that we're following here. What we're doing here is we're spiking silver nanoparticles in here, and then we're keeping track of the silver nanoparticles in here and the particles in here. If we simplify the system a bit more, then you see we have an inflow, or we have an inlet of the silver nanoparticles here in the first reactor, goes in the second reactor, goes in the third reactor, secondary clarifier, and the sludge is then recirculated here, and part of the excess sludge is withdrawn from the system here. So if we draw our boundaries and we try to model the flow of the silver nanoparticles through that wastewater treatment plant, we can simplify the wastewater treatment plant as follows. We can calculate the flow of the silver nanoparticles through the wastewater treatment plant by treating the wastewater treatment plant as a continuously stirred tank reactor. We have an inlet and we have an outlet, either a sludge in the sludge phase or in the effluent phase. For us, important is for sure we need to know which fraction goes into the sludge, so partitions in the sediment, and which fraction goes into the effluent. If you want to model this dynamically, so if you want to model a pulse or whatever, then you just do a simple mass balance, as you see what you see here, and if you solve this mass balance, you come out to a very simple differential equation. If you're interested in steady state, if you don't want to model it dynamically, then you don't need to solve this differential equation because the left term will be 0. So that's kind of the data that we analyze. But as you saw before, we need to know what are the parameters of the wastewater treatment plant, what are the inflows, what are the outflows, and based on that, we can evaluate how much silver goes into the environment via the effluent of the wastewater treatment plant. And this basically shows the results, and basically shows that we can treat the wastewater treatment plant as a continuously stirred tank reactor. You see the dashed lines are the model calculations, the diamonds and the round symbols are the model calculations, which fit very well, although it's on a logarithmic scale. The second type of experiments I'd like to show you is we try to get hold of the kinetics of the transformations. As Klaus already pointed out, it makes a big difference if we have a metallic particles or if we have a silver sulfide. And for us, it's important how fast is this transformation. So we need to get reaction rates. And one reaction that takes place in oxic surface environments or in a sewer system is the sulfidation of the silver nanoparticles, which you see here, which reacts with metal sulfides. This can be copper sulfide or zinc sulfide. It forms silver sulfides and it releases metal ions, so copper and zinc ions. To get the kinetics of these reactions, we did a series of experiments. So we reacted silver nanoparticles with different sizes, with different types and different crystallinities of zinc sulfides and copper sulfides at different concentrations. The experiments, then the results you get are these kind of pseudo first order type reactions, and you see here on the x-axis or on the y-axis the decrease of the metallic silver. On the x-axis you see the time, so you clearly see we have a decreasing metallic silver content with increasing time. Based on the slope of these curves here, which depend on the size of these straight lines here, you get the reaction rate constants, and you can relate the reaction rate constants here with the silver nanoparticle size. The same thing you can do when you just vary the concentration of copper sulfide, and you also get a set of first order type reactions as shown here. And if you plot the reaction rate constants here against the copper sulfide concentration, you see some sort of linear combination of a linear independence. Now you can lump everything together, and this is done here. We have this first order rate kinetic that I've shown here, and the rate constant here is simply dependent on the copper sulfide or on the metal sulfide concentration, and it's dependent on the size of the nanoparticles. So what we need to be, if we have this data, we can assess how long the particles will stay metallic or partially metallic in the environment, and that will be important to assess whether particles are metallic, partially sulfidized, or fully sulfidized. However, to do these calculations, we need to know the concentrations of the metal sulfides in the surface water or in the sewer system. This can be measured. Data are existing for the surface waters. And we need to know how large the particles are, and this can possibly be extracted from a repository. And then, if we know these data, we can assess the kinetics of the silver nanoparticles and therefore assess their toxic potential. So, Klaus,
Thank you.
back to you.
Yeah.